क्लास लेनी पड़ेगी। फोर्थ खोले ना
प्रिंट करके दे दी सर
प्रिंट बोले थे सर
पता नहीं शायद हम लोग
ओ मैं कंफर्म करते
हम लोग पीपीटी तो
पूछ लो ग्रुप में पूछो। Good evening, everyone. Am I audible? कितने टाइम के लिए देख रहे हो? एक रात के लिए देख रहे हो क्या? कैसे देख रहे हो? एक रात के लिए? ठीक, देख, क्लास के बाद बात करते हैं. ठीक है. Good evening, everyone. I am Shefali Agarwal. I am a research scholar at IIT Madras, and this is our last TA session on the topic of advanced concrete technology. So we have already covered about cement production, composition, chemistry, and then various components of our concrete like aggregates, different chemical admixture, mineral admixture, and then different testing to test the fresh and hardened property of concrete, then other durability properties like chemical attack. So in this last lecture we'll be starting with the durability of concrete. So as we have discussed in last week itself, the main durability issues with concrete system are corrosion, then we have chemical attack because of like sulfate attack and all, then we have alkali silica reaction which will cause formation of delayed attendant formation, and then other things are like why this type of issues happen because of transport mechanism in concrete system, and then what type of material you are using and what type of mix design we are using. And normally, unlike strength properties, we are not checking durability properties beforehand before doing mix design. So as we have stopped our last lecture on the attringite formation, so this we already discussed last time, like what are the different type of attringite forming in the concrete system. First is primary attringite, which form at the early stages because of the hydration of which element, which component? C3A. Okay. Other is late primary attringite, where more sulfates are present. Because of that, we have a late attringite formation. If you remember from our hydration curve, we will have this. We will have this kind of hydration curve which will give us late attringite formation. Then we have external attringite formation when we have due to sulfate attack, there is a chances of late attringite or delayed attringite formation. And lastly, we have delayed attringite, which is internally suppressed attringite which grow at later stages. So the next thing is, what is the attringite crystal habitat? So based on the pH value, what is the length to thickness ratio of attringite? So at the medium pH value like 11 to 12, you have a 10 to 11, you have a higher length attringite, like your, we know attringite are like needle like structure, so your length will be much more at this pH value. And this is the same thing done by different authors, and how they have told about the stability of our attringite depending on your pH value. So next thing is how attringite happen due to sulfate attack. Attringite formation happen due to sulfate attack. So how we can protect our system from sulfate attack? If we are using low C3A cement, as we were discussing before, because of use of C3A, presence of C3A, there are chances of more attringite formation. So if we are using low C3A cement, we have chances of low attringite formation, and also low C3S can help in formation of less attringite. Okay, and this is like lab test where we are doing mortar prism test for expansion, and for checking the shrinkage and expansion. So if attringite is forming, what is happening? Your sample can expand, your mortar can expand. So you can check the you can check your length change in your prism samples, uh, let's say like cycle by cycle, and that can tell you about the attringite, if attringite is forming or not, and then you can quantify it using some let's say characterization technique like XRD and all. Other thing is, first is we are using low C3 cement. Next thing is we can use high alumina cement, then we can use super sulfated cement, and we can use some mineral admixture, low water to cement ratio, and good impermeability. If we can be we can go through these all things, we can protect our system against external sulfate attack. So here if you can see different type of material, this is concrete having 12.3% C3A, this is 7.1 and 3.5% C3. You can see this white crystal forming, right? So in a low C3 cement, it is a very dense material and a less attringite formation as compared to higher C3A cement. So this is another type of testing which have been done in lab. So in this case, if you see, we are telling that with the with the percentage of attringite, your expansion, how expansion will change. So this is the result for mortar prism test. So if you have let's say 10% of attringite, then you have a lower expansion. But if you have 40% of 30% of attringite, then your expansion rate will be 1.8%. So this is a curve which we will get from mortar prism test. Other thing is how your water to cement ratio and other factors are affecting your expansion rate. So this is a PCA study which is done on the similar base, like this is your strength value, then this is your exposure rating, and here we are talking about water to cement ratio. So it is not given as in what we are using nowadays, W by water cement ratio like 0.36, 0.55 is given water US gallons per sack of cement. So based on that, how your strength is changing and how your exposure rating is changing. So if you have more C3, if you have more attringite formation, what will happen? Because of higher water, so your strength will decrease. So next thing is, what are the different tests which can be done for sulfate resistance? First test is ASTM C452, in which we are adding gypsum to the mortar bars to get 7% sulfates, and 14-day expansion is measured in this case. Next test is ASTM C1012, where our mortars are externally exposed to sodium sulfate solution after attaining 20 MPa of strength. And in this case also we are measuring expansion, and since this is an internal sulfate, so we are measuring at 14 day. In external we are measuring at 6 to 12 months. And so this is one of the two tests which we are doing for checking the sulfate resistance of our concrete system. So here again another example which is showing how water to cement ratio is changing the property of our concrete system. So in this case, if water to cement ratio is higher, you can see more white chunks forming, and at lower water to cement ratio you have a more denser concrete. So in this case you can tell more of ettringite formation and less of ettringite formation. Okay. And other thing is, from this example you can say this is an example of external sulfate attack. So because of sulfate attack, ettringite formation, crack formation, your concrete is getting deteriorated. So this is like salt crystallization, physical attack, same concept only. Because of the presence of sulfates in your soil, your there will be more formation of needle like structure which will get disposed of. Your concrete will get disturbed. Next thing is about delayed ettringite formation. So this is also a type of secondary ettringite formation. So in that case, what is happening? Because of external because of external sulfates, your presence of water, it will create some ettringite inside your concrete system, which will expand and cause cracks in your concrete. So it is mainly because of presence of moisture inside concrete and sulfate from outside the concrete system. So so in this case, what is happening? This is your mechanism of DEF. It is mainly suppressed when temperature of fresh concrete are high and in steam curing. So because of sulfates which will get soluble inside the depending on your gypsum formation, your surface will get soluble, so it will won't let your ettringite form at that point. At later stages, what will happen? These sulfates will get released from the concrete system, get into CSH, and are later carried out by moisture, and which will form the ettringite further. Okay, so that is a concept of delayed ettringite formation. So that's about your let's say sulfate attack. Next type of problem in durability is chloride attack. So in chloride attack, if you see two type of materials here. So in the first thing, you can see that your concrete system have some porous material, porous appearance of surface zone, which will promote the increase of chlorides into your concrete system. And here if you see, there is a thick more CSH forming, and your surface layer is much more thicker, which will repel the entry of chlorides into your concrete system. So this is checked using SEM analysis. And so why chloride attack is important? Any idea? So what will happen with chloride attack? Any idea? So because of entrance of chloride in concrete, your rebar can get corroded. That is the one issue with the chloride attack. Another issue is with the addition of chloride, it can bind with C3A, and if you have a higher C3 content, your chlorides can bind with C3A and can prevent the corrosion of steel rebars. Okay, so next type of issue is acid attack. Sorry, next type of issue is acid attack. So when you have concrete in your acidic environment, let's say sewer pipes and all, then there are chances of acid attack. In that case, what is happening? Mostly sulfuric acid is formed, mostly because of sulfuric acid present in your environment. What will happen? Gypsum will form, and it will reduce the strength of your structural material. and because of this there will be deterioration of your concrete system. So that is a basic concept of acid attack. So here if you see in pictorial formation what is happening in acid attack, your all the positive ions like calcium, aluminum, silicon from your concrete system will move towards the acid solution, and all your negative ions will move towards your hydrated products. So what will happen, your all the CSH hydrated products will get deteriorated and will move away from the concrete system. This will cause the loosening of the strength of your concrete system, and in turn will cause the deterioration of your concrete system. So this is another example which is showing in sewer pipe how your sulfuric acid is forming and how it is reacting with your cementitious material and causing the deterioration of your concrete system. Okay, so here also if you can see you have three zones, like say let's say this is a pier inside your what's say any sea or something. So you have three zones: atmospheric zone, tidal zone, and submerged zone. So the concrete which is fully inside the water, there won't be any problem in that case. The one which is completely outside your in the environment won't have the problem. The concrete which is in half in water, half in air, where you all the tides will come and attack on the concrete system because of high pressure, there will be a damage at this point, and also because of alternating wet and dry cycle. So there are chances of damage at that point. Okay, so that is about your chloride attack and acid attack. Next type of issue in our durability issue in our concrete system is carbonation of our concrete system. So what is happening in carbonation? Because of the presence of CO2 and water, and CO2 enter in your concrete system, this CO2 will react with calcium hydroxide and will form calcium carbonate. So what will happen, your pH of your system will reduce. Because of reduction in pH, your rebar will get uniformly corroded, which will further cause the damage to your concrete system. So how SCM will affect your carbonation? So in case of SCMs, when you are let's say using fly ash or LC3, what will happen, your initial calcium hydroxide will be less. So initially itself your depth of carbonation will be much more as compared to your OPC system. So if you can see here, it is 28 days of exposure, 56, 70, 112 different days of exposure if you use. So in case of your SCM, your depth of carbonation will be much higher than in your OPC system, because your presence of hydroxide is less. So CO2 will penetrate much faster as compared to in your OPC system. Same thing here, it has been done using MIP, that porosity have been checked. So in LC3 system, your porosity initially will be high, but with the with carbonation, your porosity will increase. Okay, same way for fly ash. In non-carbonated, carbonated, your porosity is increasing. Other thing is effect on different type of material. So using different water binder ratio, how different material are affecting the carbonation depth. Same way here, if you are using different material and different water cement ratio, so from here you can see if you have a lower water to cement ratio, your carbonatable material is much more higher, or let's say your more hydroxides are forming in that case. But same thing has been observed in other type of SCMs. Here if you see, at a lower water to binder ratio, the carbonation depth is low. At higher water to binder ratio, your carbonation depth is higher, and this effect will depend on how much dense your system is, or let's say how much hydroxide of your system have. So this is a microstructure variation. In this is uncarbonated, and then this is carbonated. So in uncarbonated you have hydroxide, and in carbonated you have calcium carbonate formation. Okay, so that is all about carbonation or other durability issue, like we talk about chloride attack and carbonation attack. All both of these durability issue will actually cause corrosion in concrete structure. Like end of the day, that is what is happening because of chloride attack and carbonation attack. So if we talk about corrosion of steel in concrete, these are the basic electrochemical cell which is forming on the, this is a steel, this is a concrete, and the point where your metal is losing electron will be the anode, where it is receiving the electron will be cathode. Through concrete it is ionic conduction, and through metal it is electronic conduction. So this is a basic electrochemical cell which will form in our concrete, let's say any system. Okay, so this will be the anodic or oxidation reaction, iron converted into iron ions, and this will be a reduction reaction where oxygen and water will convert into hydroxides. Okay, so this is the same thing which is shown here. At anode you are having anodic reaction, cathode you are having reduction reaction. And what will happen when your steel rebar is corroding, the corrosion products which are forming, oxides of iron, they are expensive in nature. So what will happen if your corrosion products increase the volume by 6 times? So if your volume of corrosion products will increase, it will start causing pressure into your concrete system and will cause cracks in the later stage. So that is the main deterioration mechanism in your concrete system due to corrosion. Other thing is, we have two type of corrosion, like we already talked about chloride and carbonation attack. In time when we have chloride attack, there is a pitting type of corrosion. When we have carbonation, there is a uniform corrosion. So I hope you remember that fact, like last we talked, like chlorides will penetrate from one point, whichever is easier path, and therefore it will form pitting corrosion. In carbonation, what is happening? Your complete concrete is being converting from hydroxide to carbonates. So what will happen? Your pH will reduce and will cause uniform corrosion. So that is the main concept of pitting and uniform corrosion. So different factors which influence the rate of corrosion is, firstly, the resistance or resistivity of your concrete system, then your diffusion coefficient, how much concrete cover is there, and then if it is easy for CO2 and chloride to penetrate through the concrete system, or let's say your diffusion coefficient only. Okay, other point is, when we talk about corrosion, we also talk about the service life estimation of your concrete system. So if you see this graph, when when there is no corrosion, when suddenly corrosion initiates, or let's say when pit is formed, till that point you have initiation phase. Once corrosion starts, then you have a propagation phase, then you repair, and then you will get the repair phase. So your point where your concrete structure is being constructed to the point where it is deteriorated fully is called as the overall service life of your system. Okay, same thing is being shown here. This is your depassivation time or initiation phase, and then further you have a propagation phase. So various critical service life parameters here are like material parameter like diffusion coefficient, threshold value, then corrosion rate, then design parameters like cover depth, environmental parameters like surface chloride buildup rate. So how other things are how different type of materials or different type of chemicals are being used to prevent corrosion. So here it is showing how your different type of steel, let's say this is stainless steel and micro composite, how different type of steel will increase your critical chloride threshold value. And here we are seeing that how different inhibitors can affect your service life or propagation or your probability of corrosion. So in case when we don't have any inhibitor, your service life will be approximately 9.2 years. With addition of different type of inhibitor, your service life is increasing. Okay, so how to calculate this type of graph? We have a software called Live 365 through which you can calculate your service life or probability of your corrosion initiation. So these are the different methods through which you can protect your system against corrosion. So some first method is galvanization. So zinc, we know zinc can be can be used as a sacrificial anode because of its lower potential value as compared to your iron. So because of more negative potential, it will corrode first and will protect iron in the same way. And other thing is cathodic protection. So in this case we are applying an external voltage or current to the steel to keep it cathodic in nature and prevent oxidation from occurring. And also if you use your zinc anode in connection with your steel rebar, that is also called as cathodic protection method. Other thing is using of stainless steel instead of normal steel or normal iron steel. You can use higher potential value steels like stainless steel. It will have a stable passive film. Then we have some innovators providing good depth and using good quality concrete with low permeability. So other than this, these are some case studies which sir might have discussed in class already. You can see the class lecture notes. So here we are talking about RCC chimney, where you can see corrosion spots and damage in your concrete system due to acid attack. And then this is some ammonium chloride building. Because of chloride attack, your rebars are getting corroded. So complete case studies had already might be discussed in class. You can check that thing. Okay, so another type of damage in our system is alkali silica reaction. What is happening in this case? Your reactive silica so your alkali is present in concrete reacts with the silica present in your aggregates. In the presence of moisture, form ASR gel, which is expensive in nature and cause the cracking in your concrete system. So mostly if you see map type of cracking, that is mostly due to alkali silica reaction. So this is a complete phenomena showing your ASR damage. So presence of alkalis in your environment, presence of silica in your aggregate. Your silica reacts with silica react with water forming SiOH or OHSi, and then these SiOH will react with your OH ions of your alkali ions in your concrete system and will form SiO negative plus water. So this SiO negative molecules will form a gel over your aggregate. Then further these gels will, if you see here, these gels will expand in nature, connect with each other and form the cracks in your concrete system. So when the cracks reaches the surface, at that point you can see some map cracking kind of thing forming over your concrete surface. So that is your alkali silica reaction. So these are how much reactive aggregate can be used in your system. So based on your ASR expansion, you can calculate percentage of reactive aggregate, and this is your permissible expansion limit. You can't go beyond this percentage of aggregates in your concrete system. So how you can protect your system against ASR? First thing is using low alkali cement and then preventing excess of moisture. Then we can use some coatings over your concrete system, so that waterproofing coating which will prevent the ingress of moisture into your concrete system. Then we can use some chemical admixture like lithium salts, which will bind the reactive silica present in your aggregates and make it a non-expensive product. Then lastly, use of mineral admixture like silica fume. So how it will help your mineralite mixture? First, it will reduce the porosity of your concrete system. Secondly, it will bind your alkalis when anhydrated gas and won't let your alkalis react with your reactive silica in your aggregates. Nice thing is about ASR only. First thing is it is a very slow reaction. It takes years to happen, and the cracks forms also are not like sudden cracks or very deep cracks. It will be irregular cracks on the surface with a map formation. And this ASR gel is mostly white in color, and you might have seen these map cracking having white powder kind of thing. So that will be mostly ASR gel. And but the problem is its expansion can be as high as 80%. Other type of damage is alkali carbonate reaction. So it is almost similar as alkali silica reaction. The only difference in this case is it is only restricted where we are using carbonate rocks like dolomites as an aggregate. So the reaction will be almost similar as ASR, and in this case what will happen, your alkali hydroxide reacts with dolomite and will form magnesium hydroxide, which is expensive in nature. Okay. Last issue, durability issue, is freeze and thaw cycle. So in freeze and thaw cycle, it is mainly happening in your hilly areas. So you have three type of failure in this case. First is your paste will fail. Second thing, your aggregate will fail, and third, which will cause cracking. Third thing is aggregate will fail, which will cause pop outs. So in case of paste failure, what will happen, your cracks will form in the paste and proceed from inward to outward. So what is happening, let's say this is your concrete system. If you have any void and water get inside your void system, so what will happen, when it will freeze, it will your ice is much more voluminous than water. When it will freeze, it will expand outward and will cause cracks in your concrete system. That is a paste failure. Same thing, if this thing is happening near to your aggregate part, it can cause D type of cracking wherever you have a joint in your, or let's say joint in your slab or concrete system. So here if you see, it is written double joint. So wherever you have joint, you will have this type of crack form, which will look like a D in your, so it will be like this, same crack will be here. So it is a D type of cracking, which is mainly aggregate failure. Last is pop outs. So because of failure of paste, what will happen, your paste will go away with time, let's say in roads and all. So your aggregates will come out from your concrete system. Okay, so that's all about week 12. We will see some question and answers. Before that, if you guys have any doubt, please feel free to ask. You can put your question in chat box also. In case there are no questions, we will see some question and answers for this week. Okay, so the first question is, state true or false. The morphology of petringite depends on the alkalinity of the surrounding environment. True or false? Anyone? Here you can see what we are talking about. Morphology of Ettringite depend on the alkalinity of the surrounding environment. So this is true. If you see here, if you have very high pH value, your uh, length to thickness ratio will be very low, but if you have pH value in between 10 to 11, you have a very high length to thickness ratio, so it will be a true statement. Okay. Okay, so the next question is, the expansion caused by the microcrystalline ettringite is dash the expansion caused by needle-like ettringite, same, more or less than. Okay, someone said more than. Okay, let's see. So it's true. When you have a microcrystalline ettringite, it will have more expansion as compared to your needle-like ettringite. Next question is, arrange the ASTM cement types in the decreasing order of C3A content. Type 2, type 3, type 4, type 3, type 2, type 4, type 4, type 3, type 2, type 2, type 4, type 3. Any guess? So if you see from this table, we are talking about C3A content, decreasing order. Which type of cement have the highest C3A content? Type 3, right? Then we have type 2, 8%, and then we have type 5, 5%. So it will be type 5, not 4, or no, it will be type 4, this one. Maybe. I will check it. I think this will be type 4. This one be 5, 4. So your answer B is correct answer. Okay. Any doubt? So the next question is, salt crystallization within the porous media is a critical durability issue. Sodium sulfate salt can exist in different forms depending on the temperature and humidity conditions. They are thanadite and mirabilite. Which of the following are true statements? Thanadite has embedded water molecules in microstructure. Conversion of mirabilite to thanadite involves volumetric expansion. Conversion from thanadite to mirabilite involves volumetric expansion, or mirabilite has embedded water molecules in the microstructure. So there was a slide on salt crystallization. Here we are talking about different forms of sodium sulfate. So based on that slide, can you tell which one is a true statement or statements? Okay, I will give you that graph. So if you see here, This is your mirabilite and this is your thenardite. Now, which is causing more volume expansion? Relative humidity, temperature, dehydration, embedded water molecule in water. So which one have water molecule, embedded water molecule? From the composition you can see mirabilite have a embedded water molecule. So D is correct option. Next is which of the following conversion will cause volumetric expansion? So if you see here, this is your mirabilite and this is your thenardite. If you are changing from thenardite to mirabilite, there is a increase in your volume expansion, right? So because of, if you see this your composition, there is an increase in the volume expansion. So option C and D are the correct answer. Is there any doubt on this question? Okay, if there are no doubt, you will see the next question. Choose the correct statement or statements from below corresponding to chloride attack. Chloride attack on the cementitious metric causes the formation of expensive products. It can reduce by the use of cement with low C3A content or high C3A content. Mineral admixture rich in aluminates show poor performance against chloride attack. So which of the statement or statements do you think is correct? Any idea? Anybody? Okay, if you remember, we talk about if there is a presence of more aluminates, more C3A, what will happen? Your chloride will bind in your concrete system. Chloride binding will happen. So which will give us third option as a correct option. It can reduce by the use of cement with high C3A content because chloride will bind in that case. Then other thing is expensive products, no, because chlorides are not reacting with your cementitious material, so it won't cause any expensive products. Last is no, same thing we are talking about as here. If you have higher aluminates, it will have higher performance against chloride attack. So only correct option is C. Is that fine? Okay, so the next question is brucite is sodium hydroxide, magnesium hydroxide, aluminium hydroxide or calcium hydroxide. It is a polymorph of which type of material? So it is a type of magnesium hydroxide. Okay. Next question is carbonation increases the strength of normal concrete but decreases the strength of concrete blended with HC. Is that true or false statement? So that graph was there, if you guys remember. It's a true statement. Okay, I didn't add it. So what will happen in normal concrete? Your calcium hydroxide, when converted to carbonates, in that case your in OPC system, your carbonates will densify your pores, so that it will increase the strength. But in case of your HCM blended concrete, what will happen here? Pores will be more. If you remember that MIP graph, you have a higher porosity in your HCM concrete, so your strength will decrease. Okay. Okay, next question is choose the correct statements corresponding to the metallic corrosion. Location which form hydroxide ions utilizes the electron is the cathode. Reduction reaction happens at the anode. Residual strains and stresses make the metallic side anodic. Steel corrosion increases the volume by about 6 times. Chloride induced corrosion generally causes uniform section loss. Any idea which statement or statements can be correct? You have to correct statement. Okay. Option D. Okay. Any other statement do you think which is correct? Okay, let's see statement by statement. The location which form hydroxide is the cathode. That is a correct statement. At anode, you are having iron convert into Fe2 ions, and at cathode, what is happening? Your water and oxygen will form hydroxide. So this is a correct statement. Reduction reaction happen at anode? Wrong. Now only we saw reduction reaction is happening at the cathode point, which will form OH ions. Residual strains and stresses. Residual strains and stresses make the metallic side anodic. Correct. If you have more stresses, that point there are higher chances of iron converting to Fe ions, so that will make it more anodic side. Steel corrosion increases volume by 6 times. You already answered that part, so this is also correct. Chloride induced corrosion generally causes uniform section loss. This is a wrong statement. Chloride will cause pitting corrosion. Okay, so the correct options are A, C and D. Is that okay? Okay, then we will see the next question. During galvanization process, the cathode is the steel, zinc or concrete. So obviously concrete cannot be cathode. In galvanization, we are providing zinc as a sacrificial anode or cathode. It will be as a sacrificial anode. So your steel will act as a cathode. Okay. Next question is passivity of stainless steel is due to presence of magnesium, zinc, cadmium or chromium. So this is a simple question. Because of presence of chromium in stainless steel, you have a higher passivity in your system. Okay, next question is two concrete columns were constructed near to a stream. Apart from the source of the aggregates, two columns are similar in aesthetic, function, composition and strength. Column A was constructed using andesite aggregate and column B using granite aggregates. Which one have a higher possibility of alkali silica reaction? So we have two type of aggregate, granite and andesite. Which one? So why, how alkali silica reaction is happening? Because of presence of reactive silica in aggregates, right? So which type of aggregates will have reactive silica present in that? So granite usually don't have any reactive silica, so it's mostly andesite type of aggregates. So which will have higher alkali silica reaction possibility? Column A. Is that clear? Okay, so the next question is choose the correct statements regarding alkali silica reaction. Mineral admixture tend to increase the chances of alkali silica reaction. As the surface area of silica particle increases, ASR gel formation decreases. Hydration of the silica gel leads to the black discoloration as it oozes out. Higher percentage of reactive aggregates can reduce the chances of ASR. Which one do you think is correct in terms of alkali silica reaction? So if you remember this graph, can you tell from this now? If you have higher percentage of reactive silica, what will happen? Reduces the chance. If you have higher percentage of reactive aggregates present, your expansion will further decrease. So it will, the D part is correct. Then we have mineral admission tend to increase the chance of ASR. This is wrong. Your alkali will reduce, also your porosity will reduce in this case. Then as the surface area of silica particle increases, ASR gel formation decreases. So this is also true statement as and then last option is hydration of silica gel leads to the black discoloration. No, initially it will be white in color and then due to the atmospheric effect it will change to black color. So answer B and D are correct option. Next question is decracking is a type of failure caused by dash due to dash. It is a type of failure caused by paste or aggregates. First thing, it is caused by aggregates. D type of failure, it is caused by aggregates and due to ASR freezing and thawing, due to freezing and thawing. So D is your correct answer. Okay. Next question is de-icing salts are sprayed on the concrete during extreme winter season in western countries. They act by reducing the boiling point of water, reducing the surface tension of water, reducing the freezing point of water, or reducing the coefficient of thermal expansion of water. Why do we pour de-icing salt on the concrete system? So if we talk about winter season, obviously we are not trying to reduce the boiling point of water, so this is a wrong option. Then salts cannot reduce the surface tension of water. It can reduce the freezing point of water. It reduces the coefficient. It cannot change the coefficient of thermal expansion. So only correct option is C. Okay. The critical distance between air voids to ensure freezing of water within the concrete without cracking is 0.2 mm, 0.002 mm, 2 mm, 0.02 mm. So I think you might not know about this thing. So here in this slide it is given that a critical distance of 0.2 mm for concrete, after that only failure will occur. So answer is A. Fine. So next question is formation of ettringite in cement concrete is always expensive in nature. True or false? So usually if we talk about our normal concrete system also, we have a little bit of ettringite formation and it is not always expensive in nature unless and until it is a delayed ettringite formation, it won't be expensive in nature. Okay. Next question is acid attack in sewers is mainly due to the formation of hydrochloric acid, sulfuric acid, acetic acid or nitric acid. Now only we talk about acid attack, which is the acid forming H2SO4. So which one of these is H2SO4? B, correct. Sulfuric acid is called as H2SO4. Delayed ettringite formation occurs mainly in cold concrete, steam cured concrete, underwater concrete, or lean mixes. So when we talked about ettringite formation, we talk about two things. One thing is C3 content, other thing is curing temperature. Right? If you remember. So in this case, which one is correct? Cold or steam cured? So mostly it is steam cured. So when your curing temperature is more than 70 degrees Celsius, there are chances of delayed ettringite formation. So B is the correct option. Okay, next question is, pozzolanic materials help prevent sulfate attack by increasing C3A, reducing permeability, increasing water to cement ratio, or promoting expansion. So answer is by reducing permeability, you can prevent external sulfate attack. Which test measures sulfate resistance in mortar bar? So we talked about different ASTM methods for sulfate resistance. So which test we were doing for mortar bar? ASTM C1012, C1202, C876, C231. So it is answer A, C1012, where we are calculating the expansion in our mortar sample at different time. The main acid form in sillage bed that attack concrete is acetic, nitric, sulfuric, or lactic. Now we are talking about sillage beds, it's not in our sewer system. So in sillage beds, mostly acetic acid is forming. Sulfuric acid will form in the sewer pipes. Corrosion rate is faster in dry concrete, moist oxygen rich concrete, submerged concrete, or carbonated concrete. Rate of corrosion we are talking only. In carbonated concrete, what will happen once your this much layer, let's say, is carbonated, so it will be much more denser, which will reduce the penetration of further ions to move towards the steel bar, so it won't be faster in this case. So mostly rate of corrosion rate is faster when you have enough moisture and oxygen present on the steel surface. Okay. Why is sulfate attack more pronounced under alternate wetting and drying? More chemical reaction time, sulfate concentration increases on drying, ettringite dissolved on wetting, or lower permeability. So when we are having alternate wetting and dry cycle, what will happen? When it is drying, your sulfate concentration will increase onto the surface. So this is your correct answer. The most damaging zone in marine concrete structure is submerged, tidal, splash, or dry zone. So we already discussed about this thing. Like you have a submerged zone, then you have dry zone. So mostly in your tidal zone or splash zone, you have a more damage. B, tidal zone. Actually, splash zone is also tidal zone only. So both are correct answer in this case. In freezing and thawing cycles, hydraulic pressure theory suggests water expansion causes tensile failure in paste. Ice forms only in large pores. Pressure is uniform in all directions. Air voids increases expansion. A. Water expansion causes tensile failure in paste. It is the correct answer. So we talk about three type of failure: paste failure, then two type of aggregate failure. So this is a paste type of failure. A basement wall shows moisture ingress and white deposit. The deposits are likely to be efflorescent due to carbonates, ettringite, rust stain, or salt scaling. So if we are talking about basement wall which have moisture ingress, in that case it is mostly, it can be salt scaling, but mainly it is efflorescent due to carbonates present in your system. Because here we are not talking about salts at all, we are just talking about normal moisture and white deposits. A water tank shows internal corrosion of reinforcement. The waterproofing type used should be negative type, positive, integral, or surface unit. So if you guys don't know about positive and negative waterproofing, let's say this is your concrete wall and then this side you have a water. So if you are providing your waterproofing at this point, you are preventing your concrete from water to ingress into the concrete. That is called as positive waterproofing. But if you are providing inside the wall, this is, let's say, your room. If you are providing inside, then this is a negative type of waterproofing, where you're preventing your room to get wet, but your concrete can get wet. So here we are talking about there is corrosion of reinforcement and waterproofing is provided. So if your reinforcement is getting corroded because of water, then mainly it is a negative side of waterproofing. Okay, waterproofing which should be used, okay, to prevent this type of corrosion we should use positive waterproofing. So if it was asked that waterproofing which is already used, then it can be negative type. Okay, so the last question is, to prevent ASR in dams using reactive aggregates, you should use low alkali cement and pozzolans, increase alkali content, reduce curing temperature, or add gypsum. So the best way to prevent ASR is use low alkali cement and pozzolans. So that's all for this last week. If you guys have any doubt in this session or anything regarding your complete syllabus, you can ask me, or you can put in chat box also, or you can mail me also. Any doubts? Okay, in case there are no doubts, then I'll close the class for today. Thank you for joining.